Thanks everyone for joining the Neon training on AOP data in GEE. We'll just do some quick introductions and then jump into a short presentation and then some live coding. We can start with you, Claire.
Yeah, just in case anyone was not here last week, I'm Claire Lunch. I'm a data scientist at Neon. I work on Neon's data processing pipelines and also on tools and resources and trainings to help people use Neon data.
And then let's jump to John Muszynski from AOP.
Hello, everybody. I'm John Muszynski. I'm one of the research scientists in AOP. I work a lot on flight planning, support in other ways, and I'll be helping Bridget a bit in this seminar.
Thanks, John. And John is also a great GEE resource. And then lastly, I'm Bridget Haas. I probably met a handful of you at the last training last week. I'm also a data scientist with both AOP on the remote sensing team and then on the data skills team working with Claire on training and resources. So we're happy to have you here today. And with that, we'll jump into it. Before we get started, I just want to briefly go over Neon's code of conduct. Hopefully most of you have seen this before since you're attending the summit, but for reference, the website is neonscience.org and then neon-code-conduct. We can drop that in the chat. And this just gives an overview of our guidelines for how we expect you to behave in any Neon-led events. So it's pretty straightforward. We ask that people be respectful and trustworthy, be direct and professional, be open and welcoming, acknowledge contributions and celebrate achievements, and then collaborate and co-create. We also have some unacceptable behavior. I won't read this all to you, but hopefully it's all pretty straightforward. And we're excited to have you at the summit next week. And switch sharing now. Okay, so before we get into the GEE, I just wanted to give a whirlwind overview of AOP, basically. For those of you who aren't as familiar, I know people are coming in at different levels of knowledge of Neon data. So this is just an image of our colorized point cloud LiDAR imagery at the Harvard Forest site at the Quabbin Reservoir. So some of the neat imagery we can get from the AOP data. And then this is AOP in a nutshell. So I'll be really fast here. Feel free to pop test questions in the chat or I can answer later. But AOP basically collects Neon's airborne remote sensing data. And we have three main data products, which are our high resolution camera data, hyperspectral data, and then our discrete and waveform LiDAR data. And all of these data products are represented at least partially in GEE. We don't have the full data product suite in GEE, but we have data from all three sensors there. So this is what our data pipeline kind of looks like, and I'll just briefly go over this so that you kind of know what data products to expect. We start with a flight planning phase that John Muszynski he leads that and determines where to fly and when and how frequently, basically. Then when we're in the field, we have flight operators and pilots that are flying over our different sites, collecting the data, which then gets shipped back to our data center, and we call that raw data level 0. And this is similar to all of the Neon data products, but for AOP, we have then 3 levels of derived products, level 1, 2, and 3. And this kind of follows the NASA format of data, where level 1 is basically the least processed. It's kind of the most raw form aside from the raw data itself. And then level 3 is the most derived. So in AOP's case, level 1 data is often delivered by the flight line and level 2 as well. And then level 3 data is tiled and mosaicked into 1 kilometer by 1 kilometer tiles. So when we're working with the data on GEE, only the level 3 data is added there. And then after the data are processed, they get pushed to our storage platform on Google Cloud, and then they get published and then are made available through the Neon Data Portal. And then the piece that's missing here is we have another little short transformation pipeline that allows us to convert our reflectance data products into the proper format for GEE. That's COG or Cloud Optimized GeoTIFF. And then we push that to GEE as well. But the data that are published will also be available on GEE. Okay, so real quick, our sampling collection requirements, because this feeds into the data quality considerations for the data. we try to fly our sites in clear skies as much as possible. That's less than 10% cloud cover. And then we fly at 1,000 meters, which allows us to get 1 meter resolution for our data. And most of our terrestrial sites have a minimum 10 km by 10 km flight box. Some of our aquatic sites are smaller if they're not co-located with the terrestrial sites. And then we fly at peak greenness as much as we can. That's where this planning comes into play. And John can explain a lot more about this, but we try to optimize our schedule so that we're hitting each site or each domain at the peak phenological greenness, and then also are flying at low cloud cover conditions. So it's a little bit of a puzzle there. And then lastly, we fly most of our lines north to south to allow for more consistency between the flight lines. So our LiDAR data is from this active LiDAR sensor, and we are able to get basically 3-dimensional point clouds, so XYZ coordinates of what we're flying over. And then from those point clouds, we can classify the points into, for example, ground points or vegetation points. And we can also colorize them by camera imagery or by elevation or other things. And then from those point clouds, we can make raster data products, which are basically interpolations of those point clouds. So these include a digital surface model that's shown on the far left. So this is basically the Earth and anything above the Earth that we're surveying, so the forest. We can strip away the trees, since we can classify those, to create a digital terrain model. And so that's what this second image here shows in the middle. And then we can essentially subtract these two to get a canopy height model. And this is kind of one of our more exciting data products, because this is also available at 1 meter resolution. And for those of you who work with satellite data, that's pretty high resolution. All three of these data products are available in Google Earth Engine. We also have slope and aspect data products that are available on the Neon data portal, but not on Earth Engine, because those can be derived fairly easily in the Earth Engine platform. Okay, so that was LiDAR in less than a minute, hopefully.
Missed the LiDAR.
Sorry, what was that? Okay, I'll continue. And then next we have our hyperspectral sensor, which provides really high spectral and spatial resolution data, providing information about the chemical properties of what we're flying over, essentially. And so for those of you who are used to working with these sensors, you'll probably recognize this spectral signature curve in the bottom right. This is the spectral signature of a healthy vegetation plant compared to burned vegetation in the red. And you can see here the visible portion of the spectrum actually only goes to about 690 nanometers. And then all of this beyond that, and then near infrared and short infrared, is what we cannot see with our naked eye. And there's a lot of information about vegetation in particular that we can't see. And so this is kind of a powerful sensor for looking at patterns in vegetation health, invasive species, lots of different things. In the upper right corner, there's what's called and actually on the left, these are both false color image. So instead of a red, green, blue band combination, which is what we're used to seeing with our naked eye, these can pop out additional properties from these higher wavelengths and provide detailed information, such as, for example, in this image, the dark purple here are burned pixels, whereas the orange are healthy vegetation. And I'll just point out both this LiDAR data and the survey here in the upper right corner were surveys over a site called the Miriam Fire in the Pacific Northwest. And this was actually a rapid response project using Neon's it's called I'm blanking on this, research support services. We changed the name of that. So in addition to the Neon sites, we do have some additional sites as well sometimes. And you can also request that on your own. Okay, so these are the suite of Neon's hyperspectral data products that we have available. And I'll just point out, we have the different levels. So level 1, again, are available by flight line. We have at sensor radiance, and then surface directional and surface bidirectional reflectance. And I'll get into what that means in a little bit, because we do have both of those available on Earth Engine, and it's important to know the difference there. Then we have a number of vegetation indices or derived products from the hyperspectral data, and those are available both in level 2 and level 3. So level 2 would be by flight line, level 3 would be tiled and mosaicked. And so these include things like albedo, FPAR, LAI, a suite of vegetation indices, including many of you may be familiar with NDVI, which is the Normalized Difference Vegetation Index. And then we also have water-specific indices. And then lastly, we have our surface bidirectional reflectance available in that tiled level 3 data product. And I'll talk about this in a bit, but we are in the process of back processing data with this BRDF correction. So depending on the year of data that you're interested in, it may be available as either directional or bidirectional. So I can get into that in a bit, but that's just something to be aware of when you're working with AOP data. And then the image on the right is, excuse me, it's just an NDVI map of one of our sites in the Pacific Northwest called McRae Creek, and there was a big fire in the southeast corner of that site that you can see highlighted here with the really low NDVI values. This image was actually derived in Earth Engine. 1 minute, my throat's getting a bit dry. So this image was derived from Earth Engine, and it's just to show the difference in the spectral resolution between the AOP data, which is shown on the left, compared to, for example, a multispectral satellite sensor such as Landsat on the right. And so you can see we're getting much higher. This is a spectral signature of the same pixel for each sensor, and we're getting much higher spectral resolution here with our AOP sensor. And so with that higher resolution, we hope there's more you can learn, for example, carrying out classification of genus or species, or looking at certain more subtle features in here. Okay, it's hard to talk about hyperspectral data without talking about clouds, because the hyperspectral sensor is a passive sensor, meaning that the energy source is from the sun. And so if there's anything in between the sun and the plane and the vegetation, such as clouds, that can obscure the signal that we're getting back, that reflectance signal. And so when our flight operators are in the plane, for every flight line that they're flying over, they're recording the sky conditions as either less than 10% cloud cover, which we call green. We kind of follow this stoplight convention. And then if it's between 10 and 50% cloud cover, they would characterize that as yellow, and then lastly, if it's greater than 50% cloud cover, they would classify that as red. And then that information actually gets passed into our data. And so that's something we'll look at in the live coding section, is how to read in that information and then filter by weather conditions. Obviously, if possible, you want to work with the green or less than 10% cloud cover data as much as possible. But yellow is also passable. And then we only fly in these really cloudy conditions if it's basically if it's the only option we have. And for example, at sites like, I think this is in Alaska on the right, that's sometimes the case. So this is what that weather information passed through to the data looks like. This was at our Wind River site, collections between 2022. It's a little bit hard to see because that one of them's covering them, but in 2022 and 2023, we got completely green weather collections, whereas in 2025, our most recent collection, we had some of these lower priority areas that do not overlap our OS boundaries in yellow conditions. And so just something to keep in mind when you're working with the hyperspectral data. And then one other thing to keep in mind, and we'll show this in a lesson coming up, is we have, just for lack of a better word, what we call these bad bands. And these are basically just portions of the spectrum that we recommend you remove when you're working with the full spectrum. We do have 426 bands, but I think we have about 380 valid bands if you remove these water vapor absorption bands that basically are not providing valid data. And then we also have some noisy bands both at the beginning and the end of our spectrum that we sometimes recommend people filter out or at least be aware of. And then I wanted to quickly mention, as far as LiDAR sensor quality control goes, we have been upgrading our LiDAR sensors over the past decade or so since we've been operating. And the thing there's a lot of information on this slide, but the thing I want to point out is that the pulse repetition rate or pulse repetition frequency here at the second to last row has rapidly increased with our newer sensors. starting in 2021, and then more recently in 2025, we acquired a new Regal sensor. And so what that means is that the pulse density, so the pulse repetition frequency is essentially how frequently the LiDAR is sending out pulses. So with our older sensors, we were only getting up to 100, this is kilohertz, so 100,000 times a second. And now we're getting up to close to 1.3 million times a second. So it's really increased. And then our pulse density, which kind of translates to resolution on the ground, has rapidly increased from 2 to 4 points per square meter. And now we're getting in the tens of points per square meter. And this really depends on also other factors such as how close the flight lines are together, how much overlap we have, the topography, things like that. So we can't put exact numbers on that pulse density, but it's just something to be aware of, that if you're working with some of our older old data collected in earlier years, maybe 2014, 2016 or something, you're probably going to get this lower point density, whereas our more recent data should be much higher. Okay. So I'd also want to mention some of our recent updates to the AOP data products, including that BRDF correction that I referenced a little bit earlier. And then some updates that we have coming soon, but not quite available yet. So first I'll touch on BRDF corrections, which are the bidirectional reflectance function. And this is basically correcting for surface reflectance anisotropy. And this basically means that objects look differently when viewed from different angles and when illuminated from different directions. So you can imagine as we're flying across the sky from south to north and north to south, and then the sun is panning across the sky, we're getting these different angles and these different illumination factors. And so the BRDF is helping correct for this. And what that looks like in the data is basically in some of our data, the directional data, as we call it, you can see some of these kind of streaks in the data. You can especially see it in the lakes here. Whereas in our newer data, our corrected data, which is now available from 2022 onward, it's really smoothed out those artifacts and improved the quality of the data. And you'll notice that we still have some of those streaks in the lakes, and that's because we don't apply the BRDF correction or glint corrections in the lakes, and we mask out those areas. So that's something to be aware of. And basically what you need to know as far as working with the data is that now we have data collected between 2022 and this year, 2025, all have those corrections applied. And we're starting to go back and back process the older data, but currently the older data is only available as directional reflectance. And you'll see that with GEE as well. And our plan for GEE is actually only to add the BRDF corrected reflectance because that's better quality. And so you'll notice that we have more complete availability for these years for our reflectance data. And we do have some directional reflectance added for the earlier years, but on a much, it's not for our entire archive. And so you can, if you're interested in that data, we can add it for you, but we're not planning to add it until it's corrected, basically. Okay. And I should also mention this, all of this work was done by our scientist, Shashi Kanduri, who I believe is on this call, and he is attending the Convergence Summit. So if you have any questions about this, he would be the person to contact. And then Shashi's also been working on plant foliar trait products from our hyperspectral data. And currently we're very close to adding a new data product, the canopy percent nitrogen, and that's basically derived from our reflectance data. And then we pulled in some of our chemistry data from our canopy foliar data product. It's one of the OS data products to model percent nitrogen for the full AOP collection. So I'll just call out Shashi again here as he developed this product, and he would be the best person to answer questions about that. Okay, almost done with the presentation part. So I just want to highlight again, hopefully a lot of you made the training last week, and we went over some of the first two ways to access NEON data. So all the data is always available through the data portal, data.neonscience.org. And then we also have an API for programmatically interacting with the portal. And so we have packages in both R and Python for interacting with the API. And then this GEE access is only currently applies to AOP data, not to the other NEON data, mostly because GEE is really focused on raster type data products. And so that's what I'll be kind of demoing in the rest of the training session here. And so we'll get into this and do a little show how you can find the data. But as of last year, all of the NEON data that we've added to GEE are publicly searchable and findable in what's called the publisher data catalog as part of GEE. And then, like I mentioned, we have a subset of the data available now. What that means is that all of our, and I'll actually jump ahead. So these are the 5 data products from AOP that we've added to GEE. And all of the canopy height model, DE, and then the RGB data should be added, with the exception of some of the 2025 data that's still being processed. And then the directional surface reflectance, so that's what I mentioned. We haven't added all of that data because we're planning to wait until we've applied the BRDF correction. And then the bidirectional surface reflectance is fairly complete up to what we've processed so far. Excuse me. So yeah, so basically not all of the data is added, but if you need to add data, we can add it. With that, I'm losing my voice, but I'll jump over to John Musinski to give a quick demo of an app that he's built to help people visualize what's available in GEE. And then after that, we'll jump into the live coding. So this QR code here, you can follow along, but I'll have John share his screen to kind of highlight the main points of this.
Okay, great. Thanks, Bridget. Okay, so if we take over, I'm going to load the URL for this particular application into the chat. And to start off, this is this web page is the Earth Engine data catalog. And as you can see here, we have at the top a series of tabs, one of which is Publisher. Can everybody see this, by the way?
Yes.
Yep.
Okay. Under Publisher, you'll have the list of, these are the data sets within Earth Engine that are curated by the individual institutions rather than Google. Everything under kind of the complete set of data sets, most of which those data sets are curated by Google, but these are independently managed. Under this, you'll find the NEON webpage, and then the individual data products under that. And I'm going to just click on one. Within this particular page, you'll have kind of the essential information you need to identify the data product, understand what the data product contains in terms of the band information, the properties that are associated with it, any kind of citations, etc. And a critical set of information here is this Earth Engine snippet, which is going to be used within the code that you'll see later to actually pull the data, the image catalog, into your script. And the reason I bring this up right now is because there is a link to this application, this Data Viewer app, here at the bottom of the description tab. So if I click on that, up will come the URL that I shared in the chat. So this app is essentially used for us internally. It's used to help us QA the data, check for quality in case there are any issues in the processing. We can kind of look at the data sets in their entirety once they're in Earth Engine. But it's also useful for people who want to explore the images that are in each of the data collections. So on the left-hand side of the screen, you have the menu dropdowns. And on the right-hand side, you have some ancillary layers that can be pulled in on top. If this is the first time you're using Earth Engine, this is essentially what you'll see within the Earth Engine code editor. You don't have access to the code editor within the app itself, but we can pull up the code editor outside of this. So here, the first thing you'll do is if you're going to use this app, you can either use the desktop version, which is the one we're looking at now, or you can pull up the mobile version either using this QR code or by clicking on this link here. Also, if you wanted to pull up the NEON data catalog, there's a link directly to that down here. So that will give you information about each of these data products in great depth. So the first thing we do is we want to select a site. I'm going to pull up a site that allows us to filter out some of the information here. The Jones Center at HOA. The next drop-down menu down will show you all of the image collections within Earth Engine. So we have the directional reflectance, bidirectional reflectance, the canopy height model, surface model, and terrain model. These are contained within the same image collection. They're different bands for each image within the same image collection. Within the app, they're distinct data sets. And then finally, the RGB camera photography. So we'll look at the reflectance data first. After we select which site and image collection we want, we will then select which year of data we want to pull up. In this case, we'll look at 2023 at Jones. And this last number here indicates the kind of the visit number for this particular site. This means that for 2023, we had visited the site 7 times, acquired data over the site 7 times. So the image is pulled up in its natural color band combinations, which are, so down here, okay, right below that, you have an option to open up a second image on top of the first image so that you could compare them. We'll skip that for a moment. Down below here, we have image filters that can be applied to both the first and the second images. And the first, we have a selection for the color combination we want to look at, or the band combinations. We can look at natural color, false color, and you can also customize your band combinations, selecting among the 426 bands which are in the images itself. These only apply to the reflectance images. They do not apply to, these filters only apply to reflectance images, do not apply to the other image collections. They will work on both these directional reflectance and the bidirectional reflectance. Down below the band combination selection, we can look at selecting, let me go back to this. We can select whether or not we want to look at all cloud cover or just those pixels which were collected under essentially cloud-free conditions or less than 10% cloud cover. And in this particular case, we can see that the entire, this particular site was collected over multiple days. Down here, we can see they were from May 2nd, 2023 to May 4th, 23. And so most of the pixels were actually collected under greater than 10% cloud cover. And these particular on one day, and then these were collected on another day under less than 10% cloud cover. In fact, it could have been the same day. It just, these were collected probably earlier in the day, and then the others might have been collected when the cloud conditions change over time. So want us to look at the metadata to fully understand which dates these data were collected under. Finally, below we have an ability to export the image to an RGB. You can select a subset of the image. I won't go and do that right now. Or you can take this visualization and pull up a sample of the actual code. Here I can copy this code here. And then if I wanted to, I can open a new script and I can paste this code into the code editor and display that same image. And then you can begin to work from there. So you can use the Data Viewer app as a jumping off point to begin to work with a particular image in your collection. See if I'm able to get back to this. Okay. I'm going to show one more site as an example, and then we'll move on from here. So this is, I'm going to select McCrae Creek. I'm going to select the 2023 image for McCrae Creek. This is an aquatic site. And then the 2025 data for the same site. I'm going to switch to a false color combination. Zoom in a bit. One thing I forgot to show you in the other image were the ancillary layers that you can display on top. These include, for a terrestrial site, the tower, airshed boundaries, the terrestrial sampling boundary, or the TOS boundary, and the terrestrial sampling plots in different colors indicating the type of plot These will not appear in an aquatic site. We just have the actual aquatic location. It's listed currently as a tower, but it's in fact the aquatic instrumented location. But in the terrestrial site, it was the actual tower location. The reason I'm pulling this up here is Bridget mentioned earlier, this site experiment had experienced wildfire. In fact, that's what we're seeing here. Pulling out this layer panel allows me to turn layers on and off. So here I'm turning the, essentially deactivating the 2025, so we can see 2023 and then 2025. One additional functionality function in this particular app is the ability to display the spectral curves. If you have multiple, either single reflectance image or multiple reflectance images open at the same time, one can pick a pixel out, click once with the mouse, and here will appear two spectral curve plots, one in this case for 2023 and one for 2025, showing kind of the change in the spectral response for the pixel that I happen to have selected. And that's about it right now. Other information on the bottom left of the side panel include whether or not your data are released or provisional, and the year that those data come from. And in addition, one can display on the back of the background, one can select the National Land Cover Database land cover, and you can select here an option to display a satellite image instead of the map in the back of your data set. So I think that pretty much covers it, Bridget. I don't know if there's anything else you wanted to cover here.
No, yeah, I think that's great, John. Thanks for giving that preview. And everything John showed here was developed in the code editor, which is what we'll get into next. And actually, Earth Engine has a really nice, a simple way of just creating apps on the fly. So I can show that in a second, but I'll go ahead and share again. Before we get into the code, I just want to point out, so John briefly showed the code editor, which uses the JavaScript language, but I want to point out that there are multiple ways to interact with Google Earth Engine, including JavaScript, which is what kind of the main way in the code editor is designed around. And then there's also a Python API for working with it. And so there are a few Python packages. And if you're more familiar with working in Python, this may be a better route for you. And at the end of this training, I'll do a quick demo of kind of our first intro lesson, but in Python, so people can get familiar with how that looks. And then more recently, I think I haven't actually explored this myself, but there's an RGEE library for working with GEE. So these are kind of the three main languages that we expect folks to work with Neon data. So there are options. And I pulled this little chart. This is actually from the RGEE GitHub page, which is linked here. And we will share these slides. So all of these links we will make available to you, but don't worry about that right now. In the developers.google.com, there's a ton of resources, more around JavaScript and Python. And so this just shows you that there's some subtle differences in how you might structure your interactions with Earth Engine. But I mostly just wanted to point out here that there's resources for working with both of these directly in Google. And at the end, I'll share more resources. I just wanted to point this out since we're getting into the code. Okay. So I'll demo this, but I just wanted to show this is kind of a nice diagram that explains, oh, sorry, I realized I'm not in presentation mode. So this explains the code editor kind of layout. And so if you're used to working with interactive development environments, such as RStudio or Spider or other ones, it should look fairly familiar where you have different panels for different things. And we'll dive into this, but I just like this diagram, and it's also in some of our lessons because it outlines kind of all of the different features. And the main difference here with the GEE code editor is, in addition to this kind of standard development environment that you have, there's also a map at the bottom, and that's used to display basically all of the products that you've generated. And this may be familiar to you. It kind of looks like the Google Maps standard display. Okay. So with that, we'll actually get into some code, and I will share I'll start from the beginning here. And hopefully you all received instructions for setting up an Earth Engine account. They have recently made both commercial and non-commercial accounts. And so probably everyone attending this event would qualify for non-commercial. So hopefully you were able to set that up. John showed this, but I'll just show a few more things. And if you just search for GEE data catalog, that's usually how I find the catalog, although of course it's a little slow right now. I think I have it pulled up somewhere else as well. Okay, so Earth Engine data catalog. He showed our data is under the publisher data set. You can also just search for it directly by typing NEON, and you'll see the first 5 data products that come up are these NEON data products. So that's another way to find it real quickly. In the publisher catalog, if you go this route, you scroll down to find our network. Let's go again to the bidirectional data set. And then John showed some of this information, so information about the description. If you keep scrolling down, there's also a little way to directly interact with the data by, all you have to do here is just click on this example code, and then it will pop up the example script for that data set. And I think you have to still run it. So in this case, we're just pulling up bidirectional data at the site Little Rock or Lear. So that's just another quick way to jump into the code. That said, I'll start us from scratch. And I think for the first couple lessons, we'll do some live coding together, and then we may jump into just more of demos. I think there's a question from Jeffrey.
Yeah, so when I click on open in code editor,
yeah,
I want to register a new project, or I'm authorized for an existing cloud project.
Okay, yeah, great question. So if you haven't been using this, in the upper right corner, this is where we link to cloud projects. And so if you haven't created a new cloud, if you don't have any cloud projects, like for example, you don't work on Google Cloud that much, that's totally fine. You can do this. You can say register a new cloud project. And then for that, you would just need to create, let's see what happens here. It's going to look different for me because I'm connected to this is actually the Neon account. And so you'll have to go through this workflow, and this is where you need to decide whether you're commercial or non-commercial. I would say you're non-commercial probably if you're using it for any sort of research. So go through that workflow. This was in what we sent out in the setup instructions. So I don't want to spend too much time on this here, especially because for me, my demo is not gonna work because I already have a Earth Engine account. But you can create a new non-commercial project, and then you would link it back here. Does that help?
Yes, thanks. I'm trying to go through it.
Okay. Well, this part will be more of an overview of the code editor, so I don't think you'll miss too much. But okay, so as I showed in that little slide, the components of the code editor, we'll just walk through it kind of slowly for those of you who aren't used to working in here. So on the top left corner, actually I'll start at the very top here. So in addition to searching for the data sets in that dataset page, you can use this search thing to browse the data catalog, or again, you could just search, Neon Capital will pull up those data products. I'll just show this real quick. You can actually pull them in directly. So for example, you can pull them in here, and then in this panel is where we have our imports. And so you could rename this. The image collection is kind of vague. Let's call this reflectance. This would be 002, which means the bidirectional reflectance. So that's one way to pull in the data. I'll just delete that for now and search for the data. In the upper right corner, we have where you link to your cloud project. So if you have your cloud project, you can register one or change to a different cloud project if you need to there. On the left side, we have 3 options here. So we have scripts. Yours may look blank here. I have kind of a number of scripts because I use this as a little bit of a scratch space. You can create a new repository, folder, or file. And then I'll just show, I'm not going to create a new one here because I have some, but if you do create a new repository, you can Google basically has a backend for GitHub. It's not the same as, sorry, a Git managed backend. It's not GitHub, but you can actually share these repositories really easily. And this is one of the kind of nice things about Earth Engine. So I'll share this repo with you after we go through a couple lessons, because I want you to actually type through with me. But this is where you would actually do that. You can say copy, or you can use a git clone command, but usually I just do this copy, and then you can copy the link. And I'll just demo this real quick. If you go to this, actually, this is the location. This Earth Engine googlesource.com. As long as you have an Earth Engine account, it says I'm not signed in. You can actually see all of the publicly available repos. And this is kind of like, you can think of this as like GitHub. While that's loading, I'll just go back, and it seems I'm a little laggy here. Okay, so here the name, and this is actually like a backend if you wanted to get a sneak peek. If you can search for, we have some Neon AOP ones. If you just search for AOP, these are actually some of my scripts, so you could pull in my repositories directly. And then we should have actually maybe that repository is not public, but we have an official Neon repository as well. But this is kind of just like a sneak peek into how Google is managing version control essentially for these scripts. Okay. So those are scripts. You can create a new script. You can just by creating a new file, and then you could actually organize it how you want, depending on where you want to put it. And then there's also documentation built in. I personally don't find this super helpful because you kind of have to know what to look for, but it's a resource here. I find the developers page on Google to be a little bit more helpful. That, or things like Stack Overflow, or even LLMs like Google Gemini or ChatGPT. And then we also have the assets tab. And so this is where data are actually stored. And you can add your own data. So you don't have to work with data that's already as part of the catalog. You can actually add a new, it has to be in GeoTIFF format. You can add your own GeoTIFFs. You can also add your own vector files, so shape files or CSV files. So you can imagine that working with Neon data, for example, or say you want to work with your own field data in addition to Neon AOP data, you could pull in shape files, for example, like a fire boundary in this way. And then you could also pull in CSV files. So for example, you could use some of the tools we learned last week to wrangle some of the OS data in either Python or R, and then create a CSV file, and then you can upload that CSV file in this way. So we don't have the non-AOP data products in GEE, but if you want to work with the two together, this is where you would go. Okay, so that's all I'll show there for now. I'll just keep it on my scripts tab. And then we'll show this once we start typing a little bit, but we have on the right-hand side, we have an inspector. This is kind of like where you would see anything that you print out, and it's useful for troubleshooting here. And I'll point that out when we start coding. And then we have the console. Actually, sorry, the console is where things get printed out. And then lastly, we have tasks. And so this is just a preview of some of what we've been doing. So we've been adding some imagery. These are actually the tasks that we've done to add some of our data sets to GEE. So it keeps a log of that, not forever, but if you're trying to ingest or export, that's where that would show up here. Okay, so let's go ahead and start with just some basics of how to read in AOP data. And you already saw a couple shortcuts that we previewed, but let's go ahead and do this from scratch, just so you kind of get used to it. So in JavaScript, and hopefully, is this screen big enough for everyone? Seems like it's okay. But just let me know if I should make it bigger. So in JavaScript, you always have to declare your variable. And actually, let's start even before that. The double slash is the comment. So we're just going to read in AOP imagery. And we'll start with the directional reflectance. And so we'll call that reflectance 001. And the reason we say 001 is because Neon uses revisions to distinguish the two different different revisions of the same data product. And so if you're familiar with the data product IDs, which hopefully you are from last week, the directional reflectance ends in, it's actually DP3.3006. You don't have to know this, but it ends in .001. So that's where that 001 is coming from, in case you're wondering. Okay, so to read in an image collection, it's just ee.image collection. And then our data are all stored in this projects, Neon, Prod, Earth Engine, and then our assets. And then our reflectance data is called HSI ref REFL 001. So that's basically all you have to do. And if you run it, if you click run up here, it's going to run the whole code. And JavaScript, unlike, for example, Python or R, you can't really chunk it out in this editor. So I ran it, but nothing's happening because I didn't do anything. I just read it in, and so there's nothing to show. You can also import this, I showed before. You could convert it into the variable up here, and then you don't have to have it declared down here. But we recommend, just for if you're sharing scripts with others, it's best to just keep all of the declarations down here. I just did Control-Z to bring that back. But just an option that you can have it imported at the top, or you can have it read it in directly, but it will give a little, it'll underline it and then give you this prompt that you can import it. Okay, so we've read in that image collection. Now, the next kind of thing we recommend people do is first figure out what data are available. And so to do that, it's a little bit weird, but we can make a variable. Actually, let's just do it here. But so let's print basically prints to the console in the same way it would. Oh, sorry, Claire, did you have a question?
There's a couple questions in the chat that
Oh, thank you.
that I don't know how to answer.
Okay, I'm not monitoring the chat, so thank you. Let me look. Okay, so okay, looks like Jeffrey is still, oh, Google Cloud Platform has been disabled. Okay. That sounds, I'm not sure we can help you troubleshoot that at the moment, but potentially John may be able to help. Sorry, Jeffrey. We can also help sort you out after the fact. Yeah, if you're working through a university account, it may provide other restrictions. So yeah, sorry about that. And then Anna is asking, is there an autocomplete in JavaScript? That's a great question. Let's try it. I haven't experienced that, John. I don't know if you have. But unlike Python, I don't think autocomplete is as much of a thing.
No, I don't think there is within the code editor here. I will try to answer questions as they come up. I'm sorry, I wasn't monitoring that.
Yeah, I
but
wasn't either.
Answer questions directly as they come up. My suggestion for people who are unable to access Earth Engine, not Google Maps, but Earth Engine through your university is to, if you have a Gmail account, you can at least temporarily try to use your Gmail account. It means essentially registering that email address with when you're going into Earth Engine to set up your cloud project. And then, you can use that for free, at least temporarily, until you're able to get university access for more official kind of academic work.
Yeah, that's a good point. And also, so your university may also have some agreement already with Earth Engine in terms of whether it's commercial or non-commercial. But if you do your personal account, you can also, there's an option for training. Like one of the categories for non-commercial is training. So you could use that. Okay. And then we also had a question, can you show again how to import this variable? So all I did is I hovered over this first line that has that kind of, it's almost like it's a spelling error. And then it pulls up this pop-up, and then I just said convert. Okay.
Yeah, typically this is not something that I typically do. It's a function that's available, but usually I will just declare as Bridget has here, just declare the new variable, which points to the image collection. And then you kind of reuse that every time you run the script. But if you just kind of don't want to type anything in, you just want to quickly check on an image collection, you can use this other option for importing.
Yeah. Okay, so next we'll continue moving on, and I'll try to answer questions, or John will try to answer questions as they come up, because we do want people to to be able to follow along. Okay, so next I'm just going to print the images that are available in this collection. And for this, we'll use a print statement, and then so we've declared our variable, and then we use this function called aggregate, if I can spell it, array, and then the system index. And this system index, don't worry too much about what it means, but basically that's what we've named the images. And so you all won't see this, but for our canopy height models, those are oh, sorry, that's not showing what I wanted to, but that's basically the year site visit of all of our data products. So let's go ahead and run this whole script again. And then now we can see on the console, some things are popping up. So the first is just that first print statement. So I printed out and actually this should be directional. I mistyped there. So I'm printing out the images in the directional reflectance. And then if I expand on this list down here, this is what that system index is. So these are basically just the names of our individual images in that image collection. And here it's sorted ascending. So our first image in this is 2013 CEPR, and that was our first collective CEPR. So as John mentioned, this is the visit number. That's the cumulative number of times we've flown each site. And we'll just scroll down to the bottom so we can see that we have data up from 2023 to 2021. But this is by no means all of the data that we've collected, and that's because we haven't added it purposefully. So let's go ahead and do the same thing, but for the bidirectional reflectance. So you can either type it out, or a shortcut would just be copy this whole thing. And we'll do the same thing for bidirectional, and we'll make a few changes here. So let's call it reflectance 002. That's our BRDR and topographic corrected reflectance data. And then here, the key point is the end number is 002. And then let's call this bi-directional. And then again, all we're doing is switching from 001 to 002. So let's run that again. Okay, so now we see directional reflectance. We already looked at that. And then here are the images in the bidirectional reflectance. So you'll see right away, our first year is 2022. And then we have data through 2025. Not all of the 2025 data is in there yet, but we're working on adding that in the next weeks and month. Okay, so that's reading in and seeing what data are available. And then you can do the same for the D and CHM and RGB collection. So basically the only thing that would change here is for the canopy height model, that's called CHM. And you can also find that here. So if you looked at the canopy height model, you can find that image path in this collection snippet. So that if you don't remember your image collection, you can just go to this is kind of a shortcut to find that. You can just copy and paste that in as well. So again, you can do that for all of the data products, but for now, we'll just focus on the reflectance data products. Okay. Now let's read in a single reflectance image for a single year site visit. So we'll look at the CLBJ site, which is the Lyndon B. Johnson grassland, I believe in Texas. Okay, so now to look at a single image and define it as a variable here. So let's call it 001 CLBJ 2021, just to be clear. So we're trying to get the surface directional reflectance from the NEON site CLBJ in 2021. And so here's where Earth Engine has a lot of really handy, I'm just going to minimize the map for now because we're not using it. But Earth Engine has really handy things for filtering data. And so you can filter by a number of things. I'll just separate it out to a new line. Oops, actually, I'll just do it here. So we can filter by the date. And here, if I want 2021, so I'll filter from January 1st, 2021 to December 31st. And then you can filter by metadata. I think if I just continue here, well, maybe not. Yeah, I thought you could just tab down, but I'll just
indent it.
Oh, thank you. Okay, so down here and then tab.
Now just fill it, you've completed. Yeah.
Oh, okay. Thank you, John. Okay, so yeah, you can continue on the next line. So for example, I thought it auto indented, but it doesn't. Okay. We can also filter by metadata properties. And so the Neon site is one of the properties. And I'll show this in a second, and then you can say equals. And so here we want the site name is CLBJ. And then this will still return an image collection, even though there's only, we happen to know there's only one image in here, but you have to use this first to pull out only a single image. And you could also do last, but in this case, we happen to know there's only one. If we look in here, scroll over. So it's for 2021 CLBJ. There's no other CLBJ. Sometimes we do have 2 flights in a year, but I'm just selecting first to pull out a single image. And then let's go ahead and just print so we can see what we create, what variable we have now. So we can print that CLBJ 2021 here. Okay, so now let's run the whole thing. And again, it's going to run everything every time. So if you don't want to always run this whole command, you can do Control/, we'll comment it out. And then I just did Control-Z to undo, but that's like a quick way to comment out. So if you want to, you can comment out lines as you go, but in this case, we need certain lines to be defined because other lines depend on them. So I'm running all of it again, and then now we can see, I didn't print what this actually was, but we can see this, okay, it's an image. It's actually showing us the direct path to that image. And then if we expand on it, here's where we can find a lot more information. So in the bands, we can see these are actually all of the reflectance bands. I mentioned that we have 426 bands, so I'm going to scroll down for a while. And then in addition to those 426 reflectance bands, we also have a number of QA bands that provide additional information. And so the ones that you may be interested to use when you're first working with the data are the weather quality indicator, and we'll show that in a little bit, and the acquisition date. And that acquisition date you may be interested in because, for example, if you collected field data or you have satellite data and you want to match it in time to the AOP data, this is where you would find that information. And then the weather quality indicator provides information about the cloud conditions during the acquisition on a pixel basis. Okay, so that's our image that we've read in, and we can also pull out some of, I'll show this real quick. So in addition to the bands, we also have properties. And so here you can see there's a number of properties associated with this image. Some are kind of self-explanatory because we already saw that we were looking at the 5th visit. So that just explicitly pulls out the visit number is 5. You can look at the description. This is actually pulled directly from our data portal, the flight year, the data product URL. So if you click on this link, it will take you to the Neon data product page. And then this is where you can find additional information such as the algorithm theoretical basis documents or ATBDs, the quick start guide. So anything about the data product that you need to know will be linked from here. We have the Neon domain, the full site name. So this is the L.B. Johnson National Grassland. And then this is kind of an important piece. This is whether the data are provisional or released. So as Claire went over in the last training last week, Neon does provide annual releases of data. AOP is a little different than the other Neon systems because we don't save all previous versions of data. And so for AOP, it's really important to pay attention to this release tag. It will either be released with the latest release year or it will be provisional. And then we have a scale factor. So the reflectance data is scaled by 1,000. To get it to a number between 0 and 1, some percentage, for example, you would have to divide by this 1,000. So that's something to keep in mind. And then we also have the sensor name and the sensor number. So we operate 3 different NIS sensors, and they should be all fairly similar, with the exception of our Hawaii sites are actually flown by the Global Airborne Observatory. And so those would actually have a non-Neon sensor. And then we have a bunch of information about the wavelength, and FWHM means full width half max. So that's basically the bandwidth. of our spectral bands. And so you can see this is where you get information about the actual band wavelength. So this is 381 nanometers. And then the full width half max is about 5.7. If you scroll down, the highest wavelength is 2510 nanometers. And then our full width half max is actually a little bit wider there. And if you're not sure what these mean, you can always go back to the data sets page and then the bands, and then there's actually a description. So here it's telling you the unit, it's unitless here, or actually the unit's embedded because in this case it's a combined thing. So it's a nanometers for the wavelength and then nanometers for the full width half max, and then the description. So this is in the visible near infrared range, and then some of the higher bands are in the near infrared or in the SWIR band range, shortwave infrared. Okay. So this is just kind of showing you where to find information about the data. And then all of these properties you can filter. So like we showed before, we're filtering by the NEON site. That was one of these properties. And then the date is also embedded in the data. Okay. So you can also read in the properties as a dictionary. We'll just show that real quick. So I'll just call it the reflectance properties, and then I'll just copy this variable. And then you can use the function toDictionary. And then if you want to look at that, you could also look only at the properties by printing out that variable. This is a little bit redundant, but it's just showing you different ways to access. So here we can see there's 438 properties, most of which are those the band information. Okay. You can pull out specific properties using a function called select. So for example, if you want to understand the release information, I'll pull out the release year. So for that, I'll take this properties variable. You could type this out too, and then select. So one of the properties here is called provisional or released. That's basically whether the data are provisional or released. And then to show that, oh, sorry, I'll call this release status. And then we can print that variable. Okay, so again, this is creating a new dictionary and it's saying, okay, it's released. And you can do the same thing for the release year, for example. Okay. So that's how you would find kind of individual information. You can filter and select on these different properties. Okay. Next, we'll just read in the red, green, and blue bands so that we can plot them. So in addition to selecting properties, you can select bands directly from the image. So if you only want to work with a subset of bands to reduce your compute, you can do it in this way as well. So select green and blue bands. And if you're not sure what is red, green, and blue, again, you can go back to this or to the properties. And so you can select which red, green, and blue. But I'll just tell you for now that the bands that we're interested in are 53, 35, and 19. So let's call this CLBJ 2021 RGB. And then that's going to be, we'll pull it from our data and then select. So here, band 053, band 035, and then, and then band 019. And then to display data, you have to set what are called visualization parameters. And so you can either do this directly when you're plotting the data or ahead of time, but sometimes it's nice to just create a variable because you might want to use it again. So here we're going to set the visualization parameters. And then this basically takes a minimum and max, and then you can use an optional gamma. We can do it with and without, but this is basically, if you're used to Python, it's more like a dictionary format. This is also a dictionary in JavaScript. So the min will set to 0, max. These are the reflectance values. So in this case, I am just presetting this to something that I know it works, but I can show you how to play around and kind of determine a better visualization parameter interactively. And then we'll set gamma to 0.8. And then, okay, then we'll do to add the layer to the map. We're basically just trying to add this RGB image to the map. You can use this map dot add layer. And so here's where we can add our red, green, and blue bands, or our subset of the bands. And if you don't want to subset the bands directly, you can also you can set the visualization parameters to read bands of interest. So, but basically if there are more than 3 bands, it doesn't know which bands to use for the red, green, and blue visualization. So then I'm going to read in my viz parameters. So you could also just use this directly in here, but it's a little bit cleaner to separate it out. And then we also give it a title. Sorry. So that's what we'll call it. And then let's run this. And actually, last thing, you can run this and actually I'll show you. And basically the problem here is it's not knowing where to center your data. So in order to center on your object of interest, you have to use either there's a map dot set center, or there's a map dot center object, the CLBJ site. So I'll use center object because it's a little bit easier. If you use set center, you have to know the lat long of your object. So if you just say center object on that, you can either use this or the full image. And then you also have to set a zoom level. So in this case, I'll use 13 because I know that is reasonable here. So let's run this again. And now you can see it's zoomed in on the site. And now we pulled in this directional reflectance data at CLBJ. And so this is kind of similar to what John was showing in the app. You can see different options over here. I've just expanded, this is the map layer. And then you can see the layers over here. You can lock the layers in place just so that this doesn't keep disappearing. And then this settings option allows you to kind of play around with this. So as I mentioned, I kind of knew what to scale into here, but if you wanted to, you can stretch. These are basically histogram stretch to change the contrast. And so you could stretch to 98% and apply. You can see that makes it a lot darker, or let's say 1 sigma. So there's different things you can play around with here. But the one I chose kind of looked closest to a true color image that I could find. So let's rerun it just to get that that rendering here. And then you can zoom in and see this is 1 meter resolution, so you can really see the data as a whole site.
Can I briefly interject?
Please do.
2 things. As far as the script is concerned, you see a lot of those little icons to the left of the line number. That indicates kind of just informational that JavaScript is expecting a semicolon at the end of each line.
Okay, yeah.
Line. So
Good
that's why
point.
you see those. If you put it's within the Earth Engine, you can work without using any semicolons at all, but JavaScript has that as an obligatory.
Yeah. Good
So-
point, John. And actually, this reminds me that I used to pretty much only program in MATLAB, and that's a MATLAB thing too. So
Yeah. The other thing is you could use the inspector, and it's completely separate. You could use the inspector tab to look at the pixel values on the image.
yeah, good point. So here, if I click here and then it pulls out, it tells me the reflectance value for the 3 bands that I pulled in. And again, remember, these are scaled. So if you divide by 1,000, that would be these are more like 0.3, 0.47, 0.17. Okay, so let's go ahead and let's read in also one of the bidirectional reflectance data, just so that, because I think that's kind of a nice comparison between the two. And then, because I'm taking a little longer than I expected, I think what I'll do is share the repo with you all in the chat, and then we'll just go through a little bit more quickly without typing out everything for the other 2 lessons, because I think it'll be nice to see kind of some of the weather and then plotting spectral signatures, but not go through it step by step per se. Okay, so let's continue on. basically what we want to do is do the same thing we just did, but with reflectance 002 and choose a different year, one of the years where the bidirectional data is available. And so we can see, I think we'll use 2022 CLBJ. Sorry, it's somewhere in here somewhere, but oh yeah, here we go. So 2022 CLBJ6, we'll try and pull in this image as well. But we don't need to do all of this stuff. We just need to basically repeat this part here. And instead of, we'll just change a few of these numbers here. So let's go down. I'll put this right below the line where we defined 2021, and we'll just change a few things. So let's look at reflectance 002. We've already defined that up here. We'll change the date to 2022, and then everything else is the same. Okay, so now we've defined our data set. We can also copy some of these, so we can use these same viz parameters. I'll just show you the other way of doing this, if I can do it on the fly. But instead of reading in the RGB image, we can read in the whole image and then just specify the bands directly in the viz parameters. So let's try to do that. Okay, so you can add another line down here. Map.add layer. And this will basically just add to that same map object that we created. And here we will do this new variable that we just created. And sorry, I should call that 2022. So let's copy in that. And then here for the viz parameters, John, I may need your help if this doesn't work, because I think you can just directly say the bands. But let's see, I'll just look this up real quick because I think, okay, so all you have to do is add up in the beginning, you can say the bands, and then you can specify those. So in that case, let's do the same bands we did before. So this is just basically an alternate way of plotting only the bands you want, but you didn't have to create a subset of the data set. And then we'll call this one CLBJ 2022 bidirectional reflectance RGB. And then let's see what happens here. Okay, so it looks like, oh, did I mess something up? Okay, so this said image is required and may not be null. So this is actually a good teaching point. So if you have errors in your code, it will pop up in red on this console. And so something I did here is not accurate. Okay, we can always go back to the other way because I'm not exactly sure what I did here. Oh, I think it's saying, yeah, it's saying, okay, actually here's another troubleshooting tip. So let's just print this to see what we get. So this is how I would go about troubleshooting. Display the, so, okay, so for some reason it's not finding the data here. Oh, and I found my issue. So here I said reflectance 001 and I should have switched this to 002. This is what happens when you copy paste. Okay, so let's rerun that. Okay, so now we can see it's pulled in both the layers, the 2022 bidirectional and then the 2021 and 2021 directional reflectance. These are just the RGB. And then as John showed before, you can select and deselect. And so this is kind of a nice representation to show how that BRDF correction is kind of smoothing out those line to line inconsistencies. Okay, so let's check the time. Yeah, I think from here, so this is actually, I know we haven't done a lot in Earth Engine so far, but compared to what it would take to make these images in Python or R, this is pretty powerful. So in Python or R, you'd basically have to download all the L3 tiles, which can be hundreds per site. And then you'd have to merge them together and plot them. And often a lot of your laptop probably wouldn't be able to do that. And so this is basically highlighting in the cloud. This makes that whole process a lot more simple. And then from here, you can start to do things like, for example, you could create geometry that's importing this geometry and then clip to that area. There's a ton of functionality kind of built in already that may allow you to work a lot more efficiently on just your area of interest. I'll go ahead and delete that because we don't actually need that for anything. Okay, so that said, I think what I'll do is share the repository with you all so that you can just follow along, and then we'll go through the next couple lessons a little bit more quickly, and then hopefully we'll have time to preview what this would look like in Python as well, because I think some of you may be interested in working in Python. So I'll just stop sharing real quick, and I'm gonna drop a link. So actually I'll show two links here. So if you click on this tiny URL, if you're already logged into Earth Engine, it basically should pop up a repository, and then you can start interacting with those scripts directly. And let me just share. And then I'll just point out that we have a whole tutorial series on this. And so if you prefer following along on the published webpage, I'll copy this as well, but you can follow along in that way as well. And there's a little bit more annotation and stuff there. Oops, that didn't work. So, okay. So hopefully if you click on this thing, let me share my screen again. Okay, so if I drop in the AOP repo, it should open up code editor, and then it should open up this AOP intro. And then you'll actually see, so the script we just ran through was this first one, AOP intro CLBJ. So we'll go ahead and jump ahead to this weather QA script, because this is showing basically how you would read in the weather information. And so the way I'll go about the rest of these is because JavaScript runs everything at once, I'm going to go ahead and just comment out the bottom part and then walk you through each step, because it'll just be a little bit faster. But I think you'll still get the gist of things. And then I'll point out at this point, so if you want to interact with people and share your code and have someone test something or vice versa, there's this really handy feature, Git link. And you can actually just copy that link, send your working code to someone else, and then they can pull up that exact code that you're working on on their end. So for example, like John and I are working together on something on GE, or he wants to show me something, that would be like a quick way we can share a code and then actually run the exact same code. So it's kind of a handy tool. And then I'll also point out here, there's this apps feature. And this is actually how, sorry, it's taking a little time to load, but this is how you can create an app. And so that's basically how John created that nice visualization app. He had all this code, and then up here, you can say new app, and then you basically can turn your code directly into an app. So we won't get into that here, but it's just a handy feature that you may be interested in.
Real quick, Control-Shift-H will give you a shortcut key to all of the different key
Thank you.
shortcuts.
Thank you. Yeah, I actually didn't know that.
So with commenting
yeah.
out, for example, I don't know if you showed how to comment out all of that.
Oh yeah. So yeah, Control/ is what I used. But yeah, thank you, John. I actually didn't know this shortcut for finding the shortcuts. So I wonder if someone had asked about autocomplete. I wonder if there's like a shortcut in here. I don't think so. But anyways, yeah, a bunch of handy shortcuts here. Thank you. Okay, so in this example, what we'll do is read in data from a different site. In this case, we'll read in data from Soap Saddle, one of our sites in California in 2019. And then the first couple steps, I'll go ahead and comment out this as well for now, are basically doing what we've already done. We're printing out, we've read in just a single image from 2019 at Soap Saddle, and then we're printing that to the console to see what we have. Okay, this should look familiar. We have our bands, we have our properties. So if you noticed in the properties, a handy way to filter for the bands is basically to exclude everything that doesn't start, oh, sorry. So we can see our bands, they all start with B001, 002, and then when we go to the bottom, we have these QA bands. And so if you only want to look at the QA bands, which we do in this example because we're interested in the weather quality indicator, you can use a little trick to basically exclude everything that starts with B. And so that's what we're going to do in this next step. I'm using Control / to uncomment that out again. And so that's what this little thing is doing. It's basically saying, select everything that doesn't start with B. And likewise, you could select only the bands by doing the reverse of this. I think that this is the part that says don't. So anyway, so what we're going to do is just pull out the QA bands. We'll run that. And so now we can see, okay, instead of all 442 bands, now we just have 16 elements. And to select a single band from there, we can again use that select. And then in this case, we know the band is called weather quality indicator. And so that's what this is doing, extracting the single weather quality indicator layer. And we can run that. Okay, so we haven't actually done anything now that we've run it. But what we may be interested in is to filter out by only the clear weather data. So that's that less than 10% cloud cover data. And so this line basically allows us to do that. So the weather quality indicator, and there should be information again in this page if you're not sure. But so you can see there's no units here. But if we scroll down, so here we see value 0 is mostly clear, 1 is partly cloudy, and then 2 is mostly cloudy. So, and then we have the colors associated with that. So basically what we want to select here, oops, I'm in the wrong place. Here, okay, sorry about that, is we want to select only the 0% cloud cover. And actually, I'm just realizing that number doesn't align, so I may need to fix the documentation. But okay, let's just go with this because we have tested this works. Okay, so now we've selected the clear weather. Again, we haven't done anything. We've just declared that variable. So let's go ahead and uncomment these next few lines here. So, and you could do a Control / to do this a little more efficiently. Okay, so now what we're doing is we're doing something called update the mask to apply that clear weather mask. So basically this is saying, determine what the clear weather data are, and then now we're masking out all the data based off of the clear weather data. And then we can also create, as we did before, a 3-band image using the red, green, and blue bands. And then we can display it and center it. And so as I mentioned before, you can either use center object or you can say set center. If you say set center, you have to specify the lat long. So you have to know that. And a quick way to do that is just to look up the Neon site. Usually this pops up the right page. And for each site, we have our field sites page. And if you scroll down, the lat long is one of the first things that you can find. So if you want to use the set center, that's usually what I do to go find that. Okay, so now we've set the center and we've added our layer. So let's go ahead and run this. Okay, so now we can see we're a little zoomed out, but this is our Soap Root Saddle site, the red, green, blue. And this is actually all of the data. We added just the RGB. We haven't, actually this should be the clear weather data. Okay, I'm not sure why this one, usually like these dark lines in here would be indicative of maybe of cloud shadowing, but looks like all of this was clear weather. Okay. So then we can define, like we did before, we defined a visualization parameters for the red, green, and blue. We can define a palette that allows us to plot the weather in green, yellow, and red. So, and I realized after I wrote this, but you can actually just use the colors green, yellow, and red. You don't have, these are the hex colors, but this should work too. Okay, and then we will uncomment this. So now we're going to add just the weather data that we read in. So that's the clear weather data. And then we're going to set the min and max in the palette. Okay, so this is basically what now I see what, I forgot this is what this is doing. So before we had filtered only to the clear weather data. And when we, let's hide the RGB for now. So this is the full Soap Root site that was collected in 2019. You can see that there was data collected in both green, yellow, and red. This typically corresponds to different priority boxes. So we try to prioritize collecting data that overlaps with the TOS data in the best weather conditions. And so, and then what we plotted was this is the data filtered to only the green data. So if we plotted the whole site, which we could do real quick, it's called SOAP reflectance. So we could just show the whole site as well. You can see that this is a quick way to just mask to only include the clear weather data. So I'll try and do that. So here we displayed the reflectance filtered to clear weather. But if we wanted to display the reflectance, all data, we can do that as well. So let's just try to do that on the fly. So I'll say map dot layer SOAP reflectance. We can use the same min and max. And then again, we have to add the bands since we didn't define the RGB here. So let's just use those. And then, so that's clear weather only. And then this will be, sorry. I think I hit insert. Okay, so all weather. And I think I have some parentheses issue. Okay, so here we go. So this is, if you wanted to show all weather as well, let's just toggle these real quick. Okay, so here we have all weather. And here you'll really notice that some of these were the data collected in red. You can see there's a lot of darker reflectance here. That's probably from cloud shadows, for example. And then we can look at only the clear weather data and then that cloud cover map. So that's kind of what we recommend as a first step, just to start exploring the data, understanding the data quality. This is where what we would recommend to start with. Okay, we only have 20 minutes left. So I think quickly I'll show this spectra plot. I'll just run through it and you'll have it for reference, just so you can see how you can plot the spectra. And then Claire, what do you think? I could do a quick demo of Python, or we could just save time for questions.
Yeah, I think maybe we can just point people to the Python resources so we have time for questions.
Okay, we'll do that. Okay, so last thing I'll just show real quick, and then again, it will always prompt you to change it. So I'm going to say abandon changes because I don't want to mess that up right now. Okay, this script, I'll just run the whole thing. But basically what this is doing is, as I mentioned before, we were selecting all the bands that don't equal B or don't start with B. So now we're selecting all the bands that start with B, and that's because these are all the reflectance data bands. And then we can select the wavelength information using, again, this is kind of like a regular expression. And then we can pull out those values. And basically what we're doing here is trying to pull out the values so that we can make that reflectance plot. And then this function is pulling out the wavelengths. And then we can make a plot. This is kind of a little bit more advanced, but you can make interactive plots using this map.onClick. And this is basically kind of what some of the code behind John's app that he demoed. But I'll just click here. Looks like there's actually an error in this. I think I renamed this. So this is like a test for you all to find the errors. Okay, let's run this. So you'll actually have to change this line. SOAP. It was called SDR, now it should be called reflectance. And then this is basically how you would pull out the information from the properties to make this wavelength versus reflectance plot. And this is that interactive spectral plot that John showed in the app and that you could make on your own. I'll fix this on the repo so that it shouldn't be a problem for you, but there was an issue originally. So in 2 seconds, that was making a spectral plot. Any questions so far on the GEE side of things? I know we didn't get into anything too advanced, and there's if you're not familiar with JavaScript, this may seem like Greek to you, but hopefully with time and with practice, you'll get used to it. And then I'll also show how you could do similar things in Python on your own. Okay. Hopefully people were able to follow.
Would you like to show the developer's webpage as a source of examples?
Yeah, I'll show that, and I have a few more slides on additional resources I was going to run through. But yeah, that's a good point. I'll pull that up. Okay, so John was mentioning there's this developer's webpage. It's developers.google.earthengine. And in here, there are a ton of resources. So guides, reference, support, community, there's community tutorials. But these guides are great places to get started. And so if you click down here, you can see they have information for both the Earth Engine code editor as well as Python. And then they have a bunch of quick starts. So again, they have those for both JavaScript and Python, and then video tutorials. And then, so yeah, this is a great place to get started. And I have linked a bunch of other resources as well. So I can show those real quick and we'll share those slides so that everyone has that information. Okay, so,
There's also another question in the chat.
oh, thank you. Okay, is weather quality carried 0, 1, 2, or 1, 2, 3 best to worst? So it's low is the best and high is the worst. And yeah, apologies. So I think the numbers that are in the dataset description are actually off, so I need to go in and change those, but I think 1 is the best and 3 is the worst. Okay, so we'll end with, yeah, and the descriptors were confusing, so sorry about that. Okay, we will end with some additional resources, and I know this is a ton of information just thrown at you, so hopefully these will be kind of where you go on your own if you start to dive into the data in Earth Engine. So I had already linked this, but we have a tutorial series for getting started with data in Earth Engine. We also taught a similar workshop at ESA this past year, and so the workshop website is linked. This has some of the same material, but it also has some kind of additional background about AOP all in one place, so that might be a nice place. If you can't find a GEE dataset, for example, some of the older reflectance data, and you want us to add it, you can email this list. That's also linked in the data product description. Okay, so we have a number of more advanced tutorials, and shout out to John here because he wrote several of these. So we have one on conducting principal component analysis on hyperspectral data, and that's basically kind of a dimensionality reduction. We have a nice lesson on linking AOP and TOS data to do species classification. And all of these, I didn't put the full link here, but all of these are under the Resources Learning Hub tutorials. And so that's just the extension at the end. And then we have a nice new lesson on spectral unmixing that we taught at the ESA workshop. And so that's linked here. We haven't put that up on the NEON webpage yet, but we plan to. And that was developed by Sam Roy, who is actually the head of the GE community catalog. And he's helped us here at NEON. And then we also have the GitHub page if you want to work directly with NEON's Data Skills GitHub page. This is where our tutorials are published from, but all of the GEE are in this folder, so that might be like a simpler way to find it. We have a number of Python GEE tutorials, as I alluded to, and apologies I didn't get time to show that today, but these first two are pretty introductory lessons. Kit Lewers, who is one of our ambassadors, made a really nice lesson on looking at AOP data along with GBIF occurrence data. And so that's kind of a nice applied lesson in Python GEE. And then this is our GitHub location for those Python GEE lessons. We also have a number of AOP tutorials outside of GEE. I'm just kind of showing those quickly here, including working with the point cloud data, because point cloud data we can't work with directly in GEE. And then Shashi, who I mentioned, also wrote a nice lesson on using discrete LiDAR to look at wildfire impacts at that SOPRU satellite site.